Good morning, everyone. Welcome to the EasyPower Tuesday Refresher Series. My name is Jim Chastain, and I welcome everyone to the discussion. The primary purpose of this series is not so much technical training as it is to maybe touch on some features and controls that seasoned users may be familiar with. Those who have not attended regional training, this may be new information, but in many cases, even long-time tool owners report that some of the features they were not aware of or had not used in many years. So in every sense of the word, it's a refresher in terms of exposure to capabilities in the tools. Sometimes we even overlook them when we're doing our regional training as far as the depth of the training. So what I want to do today is walk through the short circuit options in the ANSI short circuit module and touch on a couple places and applications where these features stand out. And as you might expect, some of the examples or some of the depth of the capabilities of the tools can get pretty technical pretty fast. And so while I welcome questions from everyone in the audience, I kind of caution you there may be some inability or maybe a need to answer some of the questions offline because in some cases it can be fairly extensive or it may be difficult to explain in kind of this one-way mode that we're in. So again, hopefully this will be useful in your use of the tools. So what I will start with first is just touching on the system setup features that affect short circuit, and this you'll see in the basic options, global options, where you want to set the base MVA so you can do a per unit calculations, set up in the case of ANSI or IAC which symbols you're going to use in your one-line diagram. And then I want to emphasize that the short circuit calculations do a full implementation of the range of ANSI C27 and C37 articles that govern short circuit calculations. And again, you're welcome to ask more specific questions as we go through this. And if there's something that comes up that you need more information on, you're more than welcome to contact tech support at a later time. Now, when we get into the short circuit focus itself, there's a unique icon referred to as short circuit options, and the tabs there are the control settings, the text output, the one-line output, and the arc flash hazard tab. We will, on next Tuesday's session, spend a lot more time on the arc flash hazard tab because it has a lot of bearing on how NFPA 70E is applied, and so we're going to basically just breeze over that in this particular discussion. And then when we get to the icons on the focus banner, there are a number of controls that are unique to short circuit and are worth understanding how their implementation applies to the calculations and how you can control displays both for phasers and for sequential components. So we're going to touch briefly on those. So let me jump out of this and jump into the EasyPower tools. And what are the things we want to start with are the basic options. So let's open up one of the sample files that's in the sample folder. This is a bigger file. When you go to a clear part of the screen and right-click, you can access the Options tab, and this gives you the ability in the system setup to set up the base MVA, the frequency that you'll be using, and then control your ANSI or IAC symbols and and your short circuit calculation method. So these are not adjustable anywhere else, and it's worth knowing how to get here. Also, the default setting for ground volts per unit is 1.45. Again, these settings affect most applications, but it's good to know where they are once you get into the details of short circuit. So as we apply this to our setup for the tools, then we go into drawing the one-line diagram, and as we complete the data entry, we're able to change focus from the database edit focus to the short circuit focus, and this is where we're going to look at the various options available. Short circuit options, so there are a number of new icons that show up when we change focus, not the least of which is the short circuit options button. And the control tab is where we'll set up the type of fault, which is duplicate of the controls on the icon bar. We can control the calculation method for X over R. It's worth noting here that the default that we recommend is the ANSI standard. There are two other calculation methods available, and frankly, these are an extension of the fact that now the calculations are being done by a computer, whereas the ANSI calculations are relatively mature and simplified. And so in some cases where an engineer wants more specificity or understands the difference, and these are all spelled out in the context help file, when you go to the user's manual and slide down to the X over R calculation type, you'll see a discussion of what the equations are involved in these calculations. So the rule of thumb is, for most of us, the ANSI standard is recommended. If you're a little bit concerned about the way the calculations are being handled for your application, if it's more complex or more strenuous, it may be worthwhile looking at either of these other two calculations. Then it is possible to control the fault filters both by area, zone, and voltage levels. So by default, we're looking at voltages from 0 to 1500 kV. If we wanted to limit this, let's say fault everything above 500 volts, we could put in a 0.5 minimum, and at that point when we faulted let me just kind of show this. When we fault the buses in the one line, in this case we don't see any calculations at all except on the high voltage side of things. And that's due to the fact that we had those filters set up. On the 480 volt side, we won't see the calculations. So again, that's a way to minimize or limit or control where you're getting data generated, and in some cases the conversion time or the calculation time that is required to exercise the tool. We also may want to set flag points for equipment duty and voltage sensitivity, and that's the purpose of these limits right here. The equipment duty threshold, if we set it -10, then it'll flag an element on the one line that's within 10% of the duty rating, and if something's within 30% of the voltage threshold, if it falls more than 30% during the calculation, it'll be flagged red. The text output is the same function as the short circuit reports, and here we can create high voltage and low voltage momentary reports, which is the same as half cycle, And based upon that being selected, we can include fuse duties or multi-case circuit breaker duties. We can create high voltage and low voltage 5-cycle reports, likewise including symmetrical and total 3-cycle outputs or duties. 30-cycle equipment duty report is something that I always want to include as I'm doing my my report outputs. And then it's not something that comes up often, but when we're doing protective duty, protective device coordination, I think it's important to consider what the voltage sensitivity report will show for remote buses. So we'll touch on that a little bit here in a second. Likewise, there's the ability to expand the verbosity of the report, and it depends upon what you want to track and how much detail you want to produce the report in. And these can get very specific, and sometimes that's not as helpful as a more brief report. So this is part of the text output. Then the one-line output gives us the ability to change the units, display units, whether we're talking symmetrical, asymmetrical, or both, the kiloamps, MVA, or per unit, and then likewise the either voltage or per unit values on remote symmetrical. The vector coordinates can be both magnitude or magnitude and angle, and then show real and imaginary values as well. So I'm going to run through a couple of these settings, and you'll notice as I selected the reports, the window reduces in size, which exposes the fact that these have been generated down here. You can expand these and save them from this location, or you can also call them up from the list of windows under our the window icon. So we see the equipment duty, the high voltage, momentary and interrupting, and then the arc flash hazard report. Arc flash hazard report is generated by default, and it was part of that short circuit report that I was looking at earlier. All right, so we're going to close these and uncheck those boxes so it won't keep reducing the window size. All right, so what I want to look at this point is specifically what I'm displaying on the one line. So we've faulted all the buses. We're looking at a half cycle momentary current. So this will be the worst case current spike during a balanced three-phase fault. We're looking at only a single phase. All three phases will be the same in a balanced fault, so it's a little bit redundant to display all of them. It makes it easier by just taking that A-phase display to be able to show the half-cycle current, the 5-cycle current, and the 30-cycle current. The significance here is if I have any motor loads, we'll see that the motor contribution to the bus fault will decline over time. So during the first half cycle, in this particular case, the motor contributed over 2,000 amps. At 5 cycles, the contribution was still over 1,500 amps, but by the time it got out to 30 cycles, then the contribution was zero. The display on the oblique is the total current on the bus, and so we see a contribution both from the utility side and from the motor contribution side during these three time frames. Now, at some point in time, it may be worthwhile to look at the sequence reports. The tool also can produce a positive sequence, negative sequence, and a zero sequence representation for that particular fault on every bus or on a specific bus. So we've just faulted the one bus, and what we're seeing is the positive sequence to be 11,200 amps, the negative sequence to be 0, and the 0 sequence to be 0. This is a fault or a fact by virtue of the fact we've selected a balanced three-phase fault. If we look at a single line to ground and fault the bus, we see zeros in this case. In fact, this is going to be a fun discussion. Whereas if we come up and fault this, we see equal currents in all three sequences. The difference being a single line to ground requires a ground return, and so if we go through and look at the one line diagram, this particular transformer doesn't have a ground attached to it, and so consequently we won't see a representation because that's not going to give us a ground return path. Whereas if this bus were to have a single line to ground, we'll see a ground return primarily from the transformer return. So if we look at this, it's worth kind of checking this out. The ground that I'm referring to is back up here on the three-winding transformer. And if we go to short circuit, single line to ground, fault the buses, we see we have contribution on the three sequential phases, or the three sequence components. We get a double line to ground, we'll have a different representation, plus, negative, and 0 sequence. And if we get a dual line to ground, now the reason it keeps giving me an informational window is that when we are utilizing the A phase or displaying the A phase for a balanced three-phase fault, we go to a single line to ground. Actually, we go to a double line to ground. It says, okay, B and C are the ones that we're going to fault. Would you like to change? And so by doing that, what we see are the B and C representations, and A will essentially be a negligible contribution to that type of fault. Whereas if we go to a line to ground fault, again, B and C are the ones that are involved in this is a dual line to line. All right, the other control on this particular row is the equipment duty report, and this is where we'll see the equipment duty threshold that was set up in the controls. And here is a device that's within 10%, and one that's and these are these are the threshold settings for medium voltage. I apologize for that. And that's the interrupting and the momentary settings for the thresholds for the breaker. Now, another extremely useful feature is the ability to do remote bus sensing. And when we go back to a three-phase fault and fault the bus, we can pick out an individual remote bus and display the contribution and the resulting voltage from this fault that we've localized on our sister bus. And so what this is telling us is that with the fault down on this bottom end of this transformer, it will impact the remote voltage on this bus by 0.05%, and the contribution of the current from each of these motors will be 200 amps that will go up through this transformer. Actually, and if we don't select a single bus and do all of them, we'll see that the contribution goes up through the main bus through two transformers. This will end up being significant when we look at the remote protective devices, because we'll have contributions to a fault that sometimes we don't expect, and it's because there are there is an impact on remote buses in both voltage and current. Now, the one area that I also wanted to touch on, so that was our one-line output. We indicate the ability to show 3, in fact, considerably higher, up to 6 decimal points with precision. There's some ambiguity in that, just because in terms of the models, there's estimates involved, and that's why we come back to different applications for the X over R calculations. In every system, as we're looking at the ratings on a bus or a breaker or a protective device, the manufacturer produces a data sheet that he reports the measurements on a specific device in a given environment, and the environment that he reports is the X over R, or power factor. And if our system has a different power factor at the point that element is in use, then some level of compensation needs to be taken into account. And so the tool does that automatically in a feature that's called Smart Duty, and it's an extension of the equipment duty display that we talked about earlier. All right, so that was the time difference, the sequential representation. If we look at, I guess the last thing I wanted to touch on was actually the three times zero sequence current for a fault in a particular location. The tool will also give us the 3 times the zero sequence current for a display, and in this case we want to have a single line to ground. And so you'll notice for this bus, what we're seeing is the total current that this bus would experience if we have a single line to ground. And so this is the 3 times the I sub 0, or zero sequence. All right, that kind of covers the controls that I was touching on. And I think with that, we'll take questions in a second. I wanted to remind folks that we have other tutorials, and built into the tool a context help and user's manual. On the website, we've announced all the training locations and dates for regional training next year, and certainly for anyone looking for additional insight or assistance with the tools, by all means contact tech support at easypower.com.